Welcome everyone. You are signed on to the Rotronic Instrument Corporation webinar, Humidity Theory, Terms, and Tips. This webinar is designed to help you make a better measurement of humidity. Better meaning more reliable, repeatable, and accurate. The first step to making a better measurement of any parameter is to understand that parameter. And that's what this webinar is about, to help you make a better measurement by understanding the parameter humidity. Everyone who registered for the webinar will receive a copy of the slides and a link to the recording. And these are delivered via email to all registrants within about 24 hours of this live broadcast. And we'll also post it on the Rotronic website. Just go to rotronic.com and go to the Measurement Academy section. Everyone's in listen-only mode. That means you cannot speak to us directly with your computer or your phone, but we do want to have you interact with us on this webinar. And the way to do that is in the questions pane. If you look at your control panel, it should be in the lower portion there. You can type in questions as they come to mind or type in comments there. And we'll have two Q&A sessions, one in the middle and one at the end, but you don't have to wait till those sessions to send in your questions. This webinar is created and produced by Rotronic Instrument Corporation. And if you don't know Rotronic, Rotronic manufactures precision measurement instruments for, of course, humidity and also carbon dioxide, low dew point, temperature, water activity, and differential pressure. And Rotronic also provides an environmental monitoring system for controlled and critical environments. We don't talk about the products during this webinar because it's educational, but of course, if you have questions or you'd like to discuss your application or the products or a good fit there, give us a call or look up your contact on the website or send us an email. We'll be delighted to discuss that at length. So again, feel free to submit your questions at any time, and we'll queue those up for the Q&A session. Speaking today, my name is Bruce McDuffie. I'm with the Rotronic Marketing Department. But don't let that deter you, because I have about 10 years of experience with humidity measurement, and I was a field sales guy for years, seen a lot of applications, did a lot of troubleshooting in the field for humidity measurement. Michael Botzkis is your co-presenter today, and Michael is the lead metrologist with Rotronic Americas, and he specializes in relative humidity and temperature measurement, and Michael's been involved in manufacturing and calibration of both humidity and temperature for about the past 19 years. Welcome, Michael.
Thanks, Bruce. It's great to be here today.
I'm looking forward to our discussion. And with that, Michael, if you could take our audience through our agenda and the takeaways we're looking for today for our audience.
So today we're going to start by looking at the common humidity parameters, so the different ways that we can measure and report the water content in our surroundings. We're also going to look for each of these, look at a few measurement tips and where we might want to use it or why we might want to use that particular parameter. We're then going to dive deeper into relative humidity in particular, because that's typically one parameter that gets used by the majority of people out there that are trying to measure water content. We'll then take a look specifically at temperature and pressure effects and how those will affect our relative humidity measurements, how they affect the relative humidity in our environments. So some of the key takeaways that we've got for everyone today is hopefully everyone will learn a little bit more about the fundamentals of humidity theory, and that's going to help support you make a better measurement. We'll get to know the different terms that you might see, and what you'll get to understand what they actually are and what they mean and what we're talking about, because we can measure water content in a number of different ways and express that value in a number of different ways, and it's good to know what that actually means for us. Hopefully you'll be able to understand whether or not you've got the right parameter for your particular application, or maybe you'll get some thoughts about another way that you could measure your application and maybe get a better result. And one of the key takeaways that we want for everyone today is to really understand the effect of temperature and pressure on our measurement systems. We'll really go into the temperature in depth, and that's one of the key things that we want people to take away from today's session. Temperature can affect our measurements. And with that, I'll pass it back over to Bruce, and I think we'll start off with a couple polls just to get to know everyone better.
Yes, that is true. And before I forget to mention it, there's 5 handouts that go nicely along with this theme and this topic of making a better measurement. If you look at your control panel, should be in the lower part, it says handouts 5 of 5. Go ahead and open that up and just download those documents. There's no registration or anything. They're just free for attendees today. And we do have a couple of polls, Michael, and it's always kind of interesting to see who else is out there in the audience. And I have 2 quick questions. The first question is, what is your industry? Just pick the industry you're working in. And if it's something else, if you don't mind, or if you're interested, just type in what that industry is in the question pane. Helps us to hone down on these, because we only get 5 choices to put in these polls. So we'll give it a few seconds here. Got refrigeration is one industry that we didn't have on there, Michael. Specialty chemical, medical devices. We should really have like 20 different offers here in this poll.
Our other usually dominates this one, and looking at the results, that seems to be where we are again.
Yep. We've got metrology, automotive, off-road equipment, mines and factories and ports and supermarkets. Wow, a lot of diversity out there today. Meteorological. Wow. Well, thanks everyone for putting those, sharing that information. And it's always great to have a good, diverse audience. Makes for more of an interactive webinar. I'm going to go ahead and close the poll, and I'll share the results with everyone so you can see. And there it is. Nobody in heavy manufacturing today. Maybe it's the description on that one, Michael. Let's see. Next, another question before we get into the presentation is asking about your level of expertise with humidity. What is your level of expertise in humidity measurement? Are you an expert enough to get the job done, or maybe this is your first exposure to humidity measurement or education about it? Give that a few seconds. Oh, got a couple of experts out there, Michael.
Good to keep us on our toes.
Someone's got to do it. Yeah. All right, I'll give it a few more seconds, folks. Thanks for sharing that. And we have a couple of quizzes throughout the webinar and a couple more polls just to keep it interactive and interesting. I'm going to close this result and share the results with everyone. Looks like most folks, enough to get the job done. Some new folks new to humidity. Good. I think we have the right mix here. And with that, I'm going to go ahead and get into the parameters. So the common humidity parameters, and there's more than these, but these are the most common ones you'll hear about. We're going to talk about relative humidity, and as Michael mentioned, we'll do a deep dive on relative humidity last from these parameters, but first we'll talk about dew point, frost point, mixing ratio, or sometimes called humidity ratio, parts per million, and then wet bulb. And we're going to get right into it here with dew point, and Michael is going to give us a definition of dew point and frost point. Michael.
Thanks, Bruce. So I think most of us are familiar with the concept of dew. We go out in the morning and quite often the grass will be wet or the ground will be wet. We didn't get rain the night before. What we're seeing is condensation forming just because the temperature got cold overnight. So dew point temperature is related to this. Dew point temperature is the temperature at which water vapor will begin to condense. And if we take that a little bit more technically, it's a temperature at which a moist gas is saturated. So it's got as much water vapor as it can hold. So fully saturated over a surface of pure liquid water. And it's important that we're over top of pure water and liquid water because that's what drives the partial pressures and the saturation vapor pressures, which determine how much moisture can be held in that space. So dew point temperature, simply the temperature at which we've got a saturated gas over water. Now, even though we are talking about a water content measurement, our units for dew point are in degrees C or degrees Fahrenheit, so it appears as a temperature measurement because we're actually reporting the temperature of the air. Now, one of the things about dew point, though, is while it is a temperature measurement, the value for dew point of a gas is not temperature dependent. So as the temperature changes, the dew point temperature does not change. It remains constant. What does change, though, is if pressure changes in a system, then the dew point temperature will change. So some people can get that confused at times, but dew point temperature is not temperature dependent. Now, there's another term that's very similar to dew point temperature, and that's frost point. Now, frost point is a temperature again, and in this case, it's the temperature at which our moist gas is saturated over a surface of ice. And there's a key difference there in that between frost point and dew point, and it's just the saturation over ice versus water. And you might say, well, isn't anything below the freezing point, 0 Celsius or 32 Fahrenheit, aren't we over ice at that point? And the answer is no. One of the interesting characteristics of water is it does not always freeze at 0 or going below 0. We get a phenomenon called supercooled water. And so we can actually have liquid water down to temperatures well below freezing. I've seen it down at -10 or -20 C, and quite often this shows up on chilled mirror hygrometers. Now, it's important for us to understand the difference between frost point and dew point because for a given temperature of frost point and dew point, it's referring to a different water content in the air. To put that into perspective, the difference between dew point and frost point at -40 is about 4 degrees C. So -4 dew point or -40 dew point is equivalent to, I believe it's about -36 frost point. So they are different, and we need to be careful in our measurement instruments to know whether it's giving us dew point or frost point, because it isn't always clear, and quite often many of them will switch from dew point to frost point automatically as it changes, as it goes below that freezing, but that's not necessarily what they're measuring. So a few things for us to understand about our dew point or frost point measurements. They are pressure dependent. So as the pressure of a system changes, we have to understand that that will affect our dew point or frost point temperatures. They are not dependent on temperature. So if we've got temperature gradients in a space, those are not going to affect the dew point or frost point temperatures. We absolutely, though, need to be careful if we're dealing with systems where the pressure changes. Dew point is quite often used in compressed air systems, and then we are definitely talking about pressure changes, so we have to be careful with that. Dew point or frost point is often used in applications where we're concerned about condensation. It's an easy way for us to understand if we're getting close to seeing condensation within our systems. We can look at the dew point temperature, look at the system temperature, and understand how much more cooling can happen before we're going to get that condensation. Very often we see it being used in very dry conditions, and this is where the difference between dew point and frost point is important. Because at those very dry conditions, quite often we're actually reporting a frost point. And we always need to be careful when the pressure changes. That is the key limitation of dew point, or one of the key concerns is pressure changes will affect our measurements. And with that, I'll pass it over to Bruce to go through mixing ratio.
Thanks, Michael. And also, folks, there's one of those documents in the handouts I mentioned. It's frequently asked questions about dew point. It's a perfect complement to the definition that Michael just did. Mixing ratio, it's the ratio of the mass of water vapor present in your system to the mass of the dry air present. So it's an absolute measure. It tells you how much water vapor is present. Doesn't care about temperature variations, doesn't care about pressure variations. Just tells you how much water vapor is present. Typically, it's reported in grams per kilogram or grains per pound. Mixing ratio is, as an absolute measurement, it's a good one for drying applications, like you see here, picture, those look like pretzels being made, or dog biscuits or something like that, where you can measure the output of the dryer or the oven, and based on the content of water vapor, you can make a correlation with the item that you're baking or drying, and correlation with the moisture content. An important note for these absolute measures, these are calculated, and they're typically calculated from relative humidity sensor, a temperature sensor, and a static pressure input. And that static pressure input is important in the calculation because the calculation will be different with different pressures. So if you buy an instrument, usually they default at 1,013 millibars, which is sea level. If you take that instrument, take it to Denver, where the pressure is usually about 840 millibars, if you don't make that change in your instrument, you'll get a very high error in your mixing ratio calculation. And that's mixing ratio. And Michael, how about wet bulb? That's one of my favorites.
Wet bulb temperature, again, we're talking about a temperature value, which is very different from our dew point or frost point values. The wet bulb temperature is giving us an indication of the cooling effect that evaporation has on a temperature sensor. So we see wet bulb being used on things like psychrometers, which we have a picture of here. And the psychrometer fundamentally has two temperature sensors on it. One to measure what's called dry bulb, which is just the ambient temperature. And then the other one is for the wet bulb temperature. And in this case here, it's this top thermometer here with the white sock on the end of it. And what the wet bulb, how these work is that sock is wet. There's pure water on it. And then the air is passed over these two sensors. In this case, the sling psychrometer is swung around to promote that airflow. And as the air flows over the sensors, the water starts to evaporate off the sock, and that evaporation takes energy, which drives down the temperature of that thermometer, and that's what gives us the wet bulb temperature. And from this, we're able to calculate what the relative humidity is using the wet bulb temperature and the dry bulb temperature. One of the big challenges with this type of measurement is that it can be very inconsistent. If we're slinging the psychrometer around at different speeds, we're not able to get a consistent airflow over it. The evaporation rates can change. So that's one of the key considerations that we need to have with the wet bulb temperatures. Quite often we can get quite large errors in them. Bruce, can I get you to just forward the slide for me? Thanks. So we see wet bulb temperature used in a couple different places. Sling psychrometers, which we don't see so much anymore, but it still gets used in some environmental chambers. If you see two temperature sensors on them, one with a sock on it and a little pool of water, they actually can use these as the control sensors for some environmental chambers. And then the other place where it's fairly common is with evaporative coolers. The wet bulb temperature gives us a good indication of how effective that cooler will be. So we'd often use these if we don't have access to power or if we want to see that cooling effect. And Bruce, I'll pass it back over to you for parts per million.
Parts per million is another absolute measure. It's telling us how much water vapor is present in the air. Once again, there's two types of parts per million, so it's important to know which one your instrument is reporting. Typically, they will report parts per million by volume, but there is another PPM, parts per million by mass. So just know which one your instrument is reporting because they actually are quite different numbers. The parts per million is good for dry gases or trace moisture. For example, at a -40° dew point, your parts per million by volume will be about, I think, about 25 ppm. So it's pretty low. As an absolute measure, it's not affected by temperature variations. It's not affected by pressure variations. And what happened to my slide switcher? There it is. And once again, ppm is calculated from our relative humidity sensor or a temperature sensor and a temperature sensor, and then a static pressure input typically. So same caution applies to parts per million. Make sure that pressure input into your instrument is in line with where you are measuring. ppm is also good for clean rooms where you need to know the actual parts per million of water vapor in the clean room. And with that, move on to the next. I think we have a couple of polls here, don't we, Michael? No, that's
Not quite yet.
not yet.
Got to introduce relative humidity first.
Okay, let's do that. Let's have a little bit of a deep dive into relative humidity. Saturation vapor pressure is one component of the calculation for relative humidity. And the reason it's so important is because saturation vapor pressure varies with temperature. And when we look at the formula for relative humidity, we'll see that saturation vapor pressure is the denominator for the equation. It's important to know that saturation vapor pressure does change with temperature variations, and the warmer the environment, the more it will change with smaller temperature variations. But even though it's a pressure parameter, it does not change with pressure variations. And we'll be talking about pressure later on. So that's the thing to take away here when we start to really drill into why temperature stability is so important. The reason is because of saturation vapor pressure. Relative humidity is the amount of water vapor present divided by the saturation vapor pressure. So it's P is the partial pressure of water vapor, which says how much water is present, and PS is the saturation vapor pressure, which varies, as we just said, by temperature. I like the bucket analogy. It kind of puts it into perspective. If we have a bucket, and the size of the bucket is analogous to the saturation vapor pressure, and the amount of water in the bucket is analogous to the partial pressure of water vapor. So in this first one here, let me put a drawing tool on. This first one here, we've got a 10-gallon bucket, and we've got 1 gallon of water in the bucket. So our relative fill is obviously 10%. Now if we go to our next bucket, now we've got a 5-gallon bucket. The amount of water vapor has not changed, but the bucket size has shrunk. And this would be the same thing as if your air cooled, the saturation vapor pressure would change. So now we have the same amount of water, 5-gallon bucket, we've got a 20% fill. If we continue to reduce the size of the bucket, or analogy is cooling the air, saturation vapor pressure changes, the bucket size changes, now we've got 100% relative fill. And all that time, the absolute amount of water did not change, but the relative fill did. If we look at it in a little bit more realistic terms than buckets, we can see the same type of analogy. We've got a 30° C air, and the partial saturation vapor pressure for 30° C is 42.4. Water vapor, amount of water vapor present, is partial pressure of 12.3 hectopascal. So 12.3 divided by 42.4, we're at 28% relative humidity. We cool down the air, the saturation vapor pressure gets lower, same amount of water, now we're at 53%. And we cool it even more, 10° C, the bucket size has shrunk, saturation vapor pressure has dropped, now we're at 100% relative humidity. And that is how you calculate relative humidity. And the reason we talk most about relative humidity is because it's the most common parameter that people measure. And we've got a poll later on to describe that. And now, Michael, I think we do have a quiz and a poll before we get into the questions. First question, which one of these is not true? Which one of these statements is not true? There's only one that's not true. And let's assume for the sake of this webinar that the last one, humidity is fun, that is true.
Might be difficult sometimes, but it's still fun.
We think so. So is the saturation vapor pressure changes with pressure? Is that true or false? Saturation vapor pressure changes with temperature. Relative humidity changes with temperature. And dew point does not change with temperature. Which of those is false? And only one of them is false. We'll give it a few seconds.
This is a tricky one because it's which one is not true.
Yep. So it takes a little more thinking, which is what we want. We love critical thinking about your measurement, especially your humidity measurement. I've got a bit of a rant on that later, but I'll try to tone it down. Okay, I'll go ahead and close the question out. We got quite a few different answers on this, Michael. The answer, the one that is false, is the first one. Saturation vapor pressure changes with pressure. That is not true. Saturation vapor does change with temperature. Relative humidity does change with temperature. And dew point does not change with temperature. So the correct answer would have been the first one. Saturation vapor pressure changes with pressure. That is not true. And I've got one more. Let me turn off that pointer. Okay. One more poll here. And this is about the parameter that you're measuring. And the question is, which parameters do you measure? And you can choose more than one here. Typically, Michael, what do we see? Relative humidity is usually the most common, but let's see if that holds for this audience.
It's typically relative humidity followed by dew point, and it'd be very interesting if people are using something else. It'd be very interesting to hear what you're using it for and where.
If you choose other, yeah, just type it into the question pane. And speaking of questions, we will be taking some questions here after this poll. So go ahead and type them in. We've got a few that have come in already, and we'll answer them. And we do have another Q&A session at the end. So if it doesn't come up in the first half, I'm sure it'll come up in the second half. I'll go ahead and close the poll. And I will share the results. And yep, relative humidity, number 1, dew point, number 2, but the absolutes, number 3. No others.
One, maybe.
Oh, 3%. Yeah, 3%. Oh, yeah, one person. Okay. David says, we measure relative humidity and calculate dew point. Fair enough. Okay, let's go ahead and do some questions. Let me hide this result. Okay, we have a question from Ted. Ted says, is there a way to measure relative humidity in superheated steam? Boy, what do you think, Michael?
I guess it depends on how hot that steam is. There are relative humidity sensors that can handle up to about 200 degrees C, but I think a lot of them, it's going to depend if that steam has oversaturated the air and you're trying to measure a value over 100%. I think a lot of instruments automatically cap themselves off at 100%. So I'd have to get back to you on that one. I don't know if there's a way to, without heating that air up even more, to make sure that you've got a value under 100%. I'm not aware off the top of my head of a way of doing that. How about you, Bruce?
Well, superheated steam, when I think of superheated steam, I think of my old Navy days when I was an engineer officer on a old steamship, and it was 1,200 psi steam running that plant. And I can tell you, there's no way you're going to measure that steam.
Yeah.
So it depends on pressure and it depends on temperature. Any steam measurement, especially if you're using a capacitive sensor, very, very difficult. Very, very difficult. They don't like that environment at all. Let's see, we have a question here. What would be the relative would the relative humidity be higher in a room that is fuller with product as compared to less? That's from Rick. What do you think, Michael? Depends on the product, right?
It depends on the product. The amount of product in a room will only affect the relative humidity depending on the characteristics of that product, and by that I'm talking about whether it's giving off moisture or absorbing moisture. Just by filling up space won't cause the relative humidity to change. All that's going to do is displace some of the air in that room. So you're not going to change the relative humidity, you're just going to have less volume of total water content in that room. So it's not going to affect the relative humidity unless there's a property about the materials that are either absorbing or desorbing water vapor.
Okay, how about this one? Can you measure humidity at pressures less than 1 millimeter mercury? From Gregory.
Yeah, there's technologies out there to measure water content in air at all sorts of different pressures. Getting down to there, you're talking about very low vapor contents in there, so you're going to have trace moisture that we're dealing with, but technically it can still be measured. Relative humidity sensors can be used in vacuums, for example. They automatically compensate for pressure because they're measuring relative humidity, but they're not the greatest for trace moisture measurements always, but there's definitely options out there for it.
Yes, agreed. Here's an interesting question from Ted. In a recirculated oven, does the static pressure of the fan influence the RH measurement? For example, it looks like 5 inches.
Yes, as the pressure changes, there will be a relative humidity change. So yes, it will affect the relative humidity because of that. I think what we typically see is that the pressures tend to equalize fairly quickly there. The increase in pressure is fairly localized to certain points. The other thing, if we're measuring relative humidity, the sensors themselves, since they're sensing relative humidity, they will still give you a proper value regardless of what the pressure is. But yeah, you could see a small relative humidity gradient in there because of the pressure changes of those fans.
Yeah, it shouldn't be too significant though at that low pressure.
No, it all depends on how fast that air is circulating
Exactly.
and how much the pressure is, what the pressure change is.
Yep, and then it comes back also to the response time of your sensor.
Yes,
If it's changing
absolutely.
fast, yeah. Okay, good questions. Thanks everybody. And we're gonna go ahead and move on to part 2 here, but these are great questions. Go ahead and keep them coming, and we will have another Q&A session towards the end of the webinar. So with that, we are going to take a deeper dive into relative humidity and the idea of why a uniform temperature is so important. Michael?
So temperature is probably the biggest influencer on relative humidity in terms of outside parameters or outside effects that can upset our measurements or create gradients in an environment that we're trying to measure. As Bruce showed you before in the saturation vapor pressure curve, as we change the temperature, the the saturation vapor pressure, or the total vapor pressure of the water that can be present, it changes. And I like to point out in this graph, it's not linear. We don't have a straight line here describing a change in temperature to a change in saturation vapor pressure. This is a very non-linear curve, and that creates all sorts of problems for us when we're trying to understand what's going on in different situations, because the temperature of our environment, even just doing it at 40 versus 20 degrees C, the temperature changes will have a different effect on us. So we've got to be careful, because relative humidity sensors, they're very sensitive to temperature. They tend to be very small and a very low thermal mass. So temperature can affect them quite easily. So we need to make sure that that sensor is at a uniform temperature, and that the temperature is representative of the environment that we're trying to measure. Otherwise, we'll end up getting a relative humidity value which is correct for where that sensor is, but might not describe what we want from our measurement environment. So Bruce showed us before in the buckets examples a very coarse way of looking at how the temperature affects us, and we wanted to look a little bit closer at what we might truly see in one of our applications. So a fairly small temperature change, what does that do to relative humidity? And for this example, we're looking at what's probably a stability chamber or some sort of environmental chamber, and we're holding it at 40 degrees C, about 54% relative humidity. So if we think back to our relative humidity formula, we know as we change the temperature, the partial pressure of the water vapor is not going to change as we change temperature. We're changing the saturation vapor pressure. So the water content in our space is not changing, just the capacity or the maximum vapor pressure is changing. So we start off at 40 C. We know we've got 54% relative humidity, 54.2 to be exact here. And so we've got a partial pressure of 40 hectopascals, and our saturation vapor pressure, if we look at the curves, we know that's 73.8 hectopascals. Now, if we go to say a bottom corner of this chamber, maybe we've got a 1 degree C drop in our environment. So what is that going to do to our relative humidity value? Well, again, we know our partial pressure has stayed the same, but now that we've got a lower temperature, the saturation vapor pressure comes down. So it's come down to about 70 hectopascals. And what that does is it means that our relative humidity, so relative to the amount that we can have present, we've got a higher amount of water content there. So our relative humidity has gone up to 57.2%. If we go to maybe up at the top corner, maybe we don't have good enough air circulation in this chamber, we see a rise of 1 degree C. So going through the same process, we can see that now we've got a relative humidity of 51.4. So I mentioned earlier that the saturation vapor pressure curve is nonlinear. We can see it even right here with temperature changes of 1 degree, depending on whether we go up or down. We either have a plus 3% relative humidity change or a minus 2.8% change. So we depending where we're at, the change in temperature can give us a different change in relative humidity. So 1 degree C changes, very common, especially if we're in a room or a warehouse. They're not even uncommon in stability chambers or small environmental changes or small environmental chambers. So we can very often see if we've got any sort of temperature gradient, we're going to have a change or a relative humidity gradient as well. Another way this shows up is in the case of we've got a chamber again here, and this is a common case where we see either a chamber where we're measuring we want to measure it with an external, a handheld probe or something, we're going and doing our measurement through an access port, or very often this is the setup we've got for a calibration of a probe. In this case, our chamber is at 40 C, 50% relative humidity, and we've got a probe going in through an access port, and our ambient conditions are 23 C, 30%. Now, if we don't get that probe inserted far enough into the chamber, or don't let it come to equilibrium, what's going to happen is the temperature at the RH sensor is going to be low, and that's just because we've got a gradient along the length of the probe. Since if a bulk of the probe is outside at 23 C and we don't have a whole lot in the chamber, we could very easily see that the RH sensor is at a lower temperature. In this example, we've just said it's 1 degree lower, and that gives us a 3% RH error. So this is one place where we can very quickly see that we need to make sure that the RH sensor has fully stabilized, come to equilibrium, and does not have any exterior temperature influences on it. Otherwise, we will get an incorrect reading. So there's a lot of causes of the temperature effect. It can be as simple as standing too close to your measurement point. Not only when we breathe do we put out a lot of water vapor, but our body temperatures can increase the local temperature. Same for holding a probe in your hand. If you're holding too close to the sensor, you're going to heat that sensor up. And if that sensor is warmer, then it's going to report a lower relative humidity. We need to make sure that if we've got the probe coming from one room to another or being put into a chamber, we need to make sure that the probe comes to equilibrium with the measurement, with the environment that we're trying to measure. This is very common for technicians if they're going site to site. Let's say the probe is in the car in the winter and it cools down. We need to give it enough time to warm up when we go into our environment to make sure we're measuring at the correct temperature. So not waiting long enough for temperatures to come to equilibrium can be a huge problem. We also need to be aware of any equipment in our environment or other sources that could create local hot spots or cold spots. Cooling fans from computers or other equipment is a very common issue that we need to deal with. We need to make sure we're not measuring in the direct output of that hot air. Otherwise, our relative humidity will read too low. Same goes if we're in the direct airflow from an HVAC system. Those are usually blowing cold air into our room. And so if we're in that direct airflow, we're going to be measuring a relative humidity that's higher than what the average is throughout the room. And Bruce, maybe you could take us through a few rules of thumb for our humidity measurements.
Absolutely. And before we do the rules of thumb, we have a quiz for the audience.
Perfect.
See if everyone's paying attention out there. This should be an easy one. I'm going to say that to put everyone on the spot. True or false? As temperature increases, relative humidity increases. Is that statement true or false? As temperature increases, relative humidity will increase. In other words, it'll go from, say, for example, 20% to 80% when that temperature goes up. True or false? And while we're doing that, we have another Q&A session coming up here in about 5 minutes, so feel free to put some more questions in there. You know, Michael, that list you just showed of possible problems with temperature, I've seen most of those out in the field. And you would think some of those just would never happen, but they do. That one about the chamber, I was at a metrology lab once, and the owner of the lab had just purchased an instrument. It was about a 12 or 18-inch probe. And he set his relative humidity, his generator, to 40 degrees C. And I don't know what the RH was. And he was complaining. He said, "You send me this new probe, and it's supposed to be calibrated, but it's not. It's way off." And I watched him do it, and sure enough, he put half of that probe in the chamber, of 40 degrees, the other half of the probe was out in the room temperature, 23 degrees, he was getting that 3-4% error.
And that's a very common issue, especially since if you did that same test at 23 degrees C, everything would read correctly because there's no temperature gradient. So a calibration setup or a test setup that works in two equal environments is very different than when you've got that temperature gradient between the two.
Exactly. So I just shared the quiz, and the answer to that is false. As you increase temperature, and that rolls me right into the rules of thumb, which I'm going to go through right now. Rule of thumb, as second bullet there, as temperature rises, RH decreases. Your environment gets relatively drier. As the temperature goes lower, as you decrease that temperature, the relative humidity will increase. Top bullet there, temperature must be uniform and representative. This is a basic rule of thumb that we're really hitting hard today. Rule of thumb, if you're having problems with your relative humidity measurement, check that bullet first. Is the temperature uniform and representative? Uniform across your probe and the area you're measuring, or representative of the area you're measuring, like the chamber example. Couple of bullets on pressure, because that's our next section, is pressure variations. Good rule of thumb is as pressure in a closed container increases, RH increases. And as pressure in a closed container decreases, RH decreases. And you could substitute RH for dew point as well. As a pressure in a closed container or a closed system like compressed air, as the pressure increases, that dew point will increase, and it will eventually approach saturation, which is the point you get water in your compressed air system. And as the pressure decreases, your dew point will also decrease. Okay, Michael, let's go ahead and talk about pressure effects.
Okay, so pressure absolutely will affect our relative humidity measurements. Now, when we were talking about temperature effects, we were looking at how temperature affects the saturation vapor pressure. When we're talking about the change in pressure of our system, we're now looking at the effect on the partial pressure of our gases. So now we're looking at the numerator of our equation rather than our denominator. So for those of you who know Dalton's law of partial pressures, we know as the total pressure in a system changes, so do the partial pressures of all the gases within that system. And it's a direct relation. If we double the total pressure, we double all the partial pressures. And I'm assuming we're keeping all the, we're in a closed system, and so we're not allowing gases to move around. So if we just take a set volume of gas, pressurize it, all our partial pressures are going to go up, directly related to how the pressure goes up. So in this case, we change the pressure, the total pressure, our partial pressure is going to increase, but our saturation vapor pressure stays the same. And this is what causes the change in relative humidity. So pressure affects us different ways depending on what we're actually measuring or trying to report. A change in pressure absolutely will change our relative humidity, but we don't always need to be as worried about changes in pressure as we are changes in temperature. The changes in temperature are far more likely to affect our actual measurements, whereas pressure not always as much. So if we're doing a relative humidity measurement, we may not need to be as worried about what the absolute pressure is in our environment. In a room, typically we're going to have fairly constant pressures, so we don't often need to worry about any pressure gradients. And if we're using a capacitive sensor, those measure relative humidity directly, so they're already compensating for whatever the pressure is in that system. If though we are measuring dew point and calculating relative humidity, it's very critical that we know what the pressure of our system is. Otherwise, we will get an incorrect relative humidity measurement. So that's where pressure can become very important for us to understand and know within our system. Dew point, yes, absolutely, pressure will affect our dew point measurements. If we're talking about wet bulb temperature, again, as the pressure changes, so does our relative humidity, and that will affect our wet bulb temperature. The evaporation rate will change. When we get into mixing ratios and parts per million, changes in pressure don't change those. But again, since they're typically calculated values, it's important for us to make sure that we know what the pressure is so that we can calculate the correct values. And I'll pass it back to Bruce now to go through a few tips for taking pressure into account in our measurements.
Basically, I guess bottom line when it comes to pressure, if you're measuring you have a relative humidity sensor, you're measuring relative humidity in an open room or an open chamber or some type of outdoors open environment, you don't have to worry about pressure. It's going to be basically, the sensor is going to give you a true relative humidity. If you're calculating one of the absolutes, then as I mentioned earlier, you have to make sure the pressure, the usually barometric pressure, is accurate depending on where you're located, what elevation basically. If you're measuring dew point in a compressed air system, which is a closed system and the pressure can vary, then absolutely you have to be aware of where you're measuring, the pressure. Are you measuring in the pressure in the line? And is your instrument then, or are you measuring with a sample off of the line that's actually expanded? If you're doing that, you've got to make a calculation to get the right dew point. It's, for example, I've seen this happen too, where people take a sample off their compressed air line, they measure the dew point at the ambient pressure, and it looks great because remember, lower pressure, you get a lower dew point. So it looks great, and they think their system is nice and dry, but they didn't make the calculation, which it's not going to be, it may not be as good, and it may not be sufficient to prevent water. So those are some tips for pressure with your day-to-day measurements of humidity parameters. And we have one quiz here before we go into the, I think we go into the final, before we go into the summary. And this is a question about pressure. True or false? As pressure decreases, dew point temperature increases. I even have the slide up here still. I guess it doesn't specifically say that, but so true or false? As the pressure decreases, the dew point temperature increases and approaches saturation. Is that true or false? As the pressure decreases, dew point temperature increases and goes up and approaches saturation. Give it a few more seconds. You guys who get this right will refund your invoice. Oh no, we didn't charge for this one. Okay. All right, I'm going to go ahead and close it out. Share the results. The answer is false. As pressure decreases, your dew point temperature goes down and your system gets drier. That's the rule of thumb. As pressure decreases, dew point decreases, you get drier, relatively speaking. As pressure increases, dew point temperature goes up and approaches saturation. And now, Michael, let's go ahead and have a summary and hit those takeaways again.
Okay, so hopefully everyone was able to understand a few more of the different parameters that we've got available to us, both for measuring the water content in a gas, as well as how to report it between an absolute and some of the other values. So hopefully those terms are a little bit more clear to everyone, and you can understand what actual parameter they're describing and what characteristic they're describing. And maybe you can see for your given applications, maybe there's a different parameter that would be more useful or could tell you more about the environment that you're trying to measure. And then one of the key things that we really want to hammer home on this presentation is there is a huge effect that temperature gradients can have on our relative humidity measurements. And if you want to have a good understanding of what's going on in your environment, it's critical that you know what's going on in terms of temperature. Unless you know what's happening with temperature, you can't really know what's happening with relative humidity. And with that, we'll go into the questions.
Right. So folks, it's to reemphasize what Michael just said, it's temperature, temperature, and temperature. Just like the old real estate, location, location, location. If you're measuring relative humidity, it's temperature, temperature, and temperature.
Yep.
We do have a couple of questions coming in, and we've got time for a few questions. So first question is from Daniel. He said, we measure using a small contained chamber with salt solutions. Are there any concerns once the sensor is installed in a large environmental chamber with a large volume area?
I'm going to assume here that Daniel's talking about calibrating his sensors in a small saturated salt chamber and then going in and installing that sensor into a larger environmental chamber. Really, there's two things here that are totally separate. Really, there's no concern calibrating in a small environment and then going and measuring in a larger environment. That sensor will still have the same uncertainties associated to it in the calibration chamber as in the environmental chamber. What you need to understand, though, is the temperature gradients within the small chamber as part of the calibration of that sensor, so that you understand the uncertainty of the measurement of that sensor. And then also understand in your larger environmental chamber, your sensor is measuring at a particular point in that chamber. If there's big temperature gradients throughout that chamber, there will be relative humidity gradients. So if you're trying to ensure that you're staying within a set humidity range, it's important that the chamber's mapped out for temperature, and from that you can measure out what the humidity gradients are. But otherwise, just going and calibrating in a small chamber and then measuring in a large chamber, there's absolutely no issues with that.
Okay, good. How about this one from Jonathan? Does airflow affect relative humidity measurements? And then he goes on to say, assuming all the air is the same relative humidity and temperature, does the flow affect the sensor's readings?
It's a very good question, and the answer is yes. And it's because all sensors have a response time. If the air is very stagnant and not flowing over the sensor, then we're not going to get a good reading, or it could take longer for that sensor to come to equilibrium. In the case of a chilled mirror, for example, there must always be air flowing over the sensor or over the sensor head. Otherwise, it doesn't have the ability to condense any of that vapor. So the airflow is not going to change what the absolute value of the relative humidity is, but it's going to affect the response time of the sensors themselves. So from that perspective, it is important.
Okay, this one is from Ashfakur. I'm sorry if I mispronounced. What should be the best solution for measuring relative humidity and temperature on a manufacturing hallway? I imagine manufacturing floor and warehouse, and what type of sensor to use? Actually, I'm going to put a plug in here. Our next webinar is about humidity measurement technology and where to use it. So unless you have a comment on that, Michael, I'll refer to the next webinar.
Yeah, I think the key question there is, what are the requirements? So how accurate do you need to know the relative humidity value? And that's going to determine what the best sensor and solution for you is going to be.
Okay, great questions, folks. I'm sorry that we don't get a chance. There's a few more here that we didn't get to, and we will reply to those via email. And as I mentioned, the next webinar, we have two webinars coming up. The next one is on the humidity measurement technology, pros and cons. And we'll be talking about technology that measures the different parameters that we went over today. And that's on December 21st. So everyone should be just nice winding down, ready for a nice humidity webinar. And the next one is how to choose the best fit humidity instrument. So these two will go hand in hand. That's on January 18th. So thank you everybody for attending today and spending time with us. We appreciate that. And I hope you got a lot of value. And I hope your humidity measurements improve dramatically. And thanks, Michael, for those great answers and presentations.
Thank you, Bruce, and thanks everyone for attending.